Shravan, hi again.
Hi again.
Long time no see.
No, I'm here in the morning.
Yeah,
You
no,
were-
I'm joking.
Yeah. I'm just reviewing a paper I don't like.
Our?
Right?
You mean our draft?
Not the hours. I just got to
You got to
read.
review some paper.
Yeah.
You
I
can share
already
screen.
right?
You can share screen. We will help you.
Yeah, it's I don't know why people are inventing complicated models. Wait a minute.
I mean, look at yourself. A lot of higher derivatives, terms here and there. Come on, I mean,
No. We have a strong point.
but those people also. So.
We have definitely a strong point.
Yes, for sure. But I tell you, I think everyone who is writing paper believes he has a very strong point, the strongest one. So.
No, the motivation is to be something. I mean, a lot of people write some model with a motivation saying that why not this model, why not this. I think why not is not a motivation. Motivation should be something more deeper and longer. Then why not to consider this?
Hello, Richard.
Hi, I wonder if I could get the revised schedule for today. It seems like we're not following the published schedule.
Yeah.
Why?
Well, let's see. It called for the session to begin at 7:15.
No, it's not like 7:15. It's just in the line of 7:15 chair is written. It's just maybe it's a bit
I
confusing.
see. So it begins at 8, and
yes.
And then goes to 8:45, and I'm up at 9:30.
Yeah.
Can I just take advantage of this time before we start to check and see whether my screen will share?
Yeah, you can do it. Yeah, sure.
Okay.
Right now.
Let me try and do that, so we don't have any problems.
Yeah, you started sharing, so it's.
That playing.
Yeah, everything is seen perfectly. So.
Okay, I'll just get out of that then.
But you don't have Mac. This is a big advantage. It looks like
you don't have what?
It looks like you don't use Mac, which is a big advantage here.
Oh, yes, that's right.
People who use Mac, they usually have some strange behavior.
I see. Okay.
Okay, good.
So I'll just mute and stop video for the time being.
Okay.
Mac and Linux, there's no difference. They're the same machines.
What?
Mac and Linux, they have no difference, almost the same. Windows is totally different machine.
I don't know.
Also, Anna is using Mac, right?
Yes.
You see, a lot of your friends are using Mac. So.
But then what? It doesn't mean that I like Mac, okay?
Well, sometimes you have no choice.
Yeah.
Why?
They gave me Mac at Imperial College, and it was hard to resist from taking it.
No, you see, with Mac, there is a way around. Actually, I can just install Linux on Mac. There is no issue about this.
But it works. I mean, Mac system works better than Linux. In the computer.
Well,
Well,
it depends on the taste and what you need from it, but for some basic things like
it's
writing
like,
code,
it's like Chinese food is better than Indian food, they're all good, but different. No choice here. It's simply
well, you need
preference.
to learn a little bit some features, how to do this and that, but then you're good to go.
This, like, I remember friends of mine were discussing just a photo camera, and then they came to a very simple conclusion that it practically doesn't matter too much which camera they use, but the most important in which hands it is. So it's like you can adjust everything, I believe. So I want to say that actually I liked the previous session, this fantastic question about ghost and ADS-CFT. We should discuss it later, Anna, with you. It is a fantastic question. It's related to the paper by Hertog. Very, very nice paper, which we read once with you, actually. I don't remember in which setting. Most likely we were in some coffee break or whatever, in some workshop or something like this. We were discussing with you a paper of Hertog about there. It was that idea that if you want to claim that some gravity modification is good, then you construct a holographic dual of one dimension less. And if that one can be claimed to be good, then it's okay. And now I think that it is indeed a troublesome question. What can be a ghost in any theory of gravity mapped to?
Is it that straightforward?
The straightforward what?
To do the mapping of
Not at all. Not at all, because usually you don't map a ghost or whatever, you map some process. It's not like you map one particle to one particle. It's like you map some state or, how to say this? You map some infrared solution of gravity to something ultraviolet in your theory, but all in your gravity will somehow be affected with the presence of this ghost anyway. So it's not like correct to say that ghost can be mapped to something, but it's correct to say that it will influence all the picture.
By the way, ghost is first of all, even if it's non-unitary or whatever, but it's still some representation with spin 2 of ADS in this case, I guess. Does
What-
it mean that is it, I'm not an expert in algebra of all that, but I don't know if it happen if the algebra is closed. I mean, if you don't need higher spins, if you have already ghost with spin 2, massive spin 2.
So whatever it is, it seems to be like a very, very interesting question, actually.
And what do you want to do with ADS?
What?
What do you want to do with ADS? Are you saying the ghost can be good in ADS?
No, I don't say it can be good in ADS, but definitely it will be mapped to something. Presence of it will influence holographic dual. So the question is, if you have 5-dimensional ADS as a background of your or even 4-dimensional, doesn't matter. You can take
Four-dimensional to
it,
3D CFT tool.
yes, you can map a 4-dimensional ADS to 3-dimensional field theory, whatever it is, okay? But then definitely presence of ghost will change you this mapping and alter it. Maybe strongly, because you will have to map something like stress energy tensor or whatever, so it will be a messy thing. Definitely all these people from ADS, they would not like to have a ghost in the spectrum, okay?
Normally they want unitarity, of course, it's one of the conditions.
Yes. Yes.
That's the reason QGC is popular, because it's nice space-time to do the mapping in the bulk and the
I'm not
model.
sure. Yeah,
No, here is there is no question of popularity and mapping. Here there is a good point that if you have this, and if you try to construct a holographic dual, how much good or maybe pathological will be the corresponding theory. And the point of Thomas here, Thomas Hertog put a very simple point. If this dual is pathologic, your original gravity is wrong. Period.
Well, don't forget that it's all about ADS, and the limit to flat space is not precisely.
No, it's another story, but still.
There are many stories, actually.
No, there are many questions, but still, non-unitary.
Are you sure that the ghost, then when you go to ADS, the ghost remains to be the ghost? By the way, I don't know.
Most likely, yes. To take lambda ridiculously small and be happy about this, it will be nearly the same ghost.
Are you sure? I think we discussed this point, that the limit is different.
No, limit can be, no, I believe that, no, you see, at least you will have, no, I mean, no matter what it will be, but it should, no, first of all, it should be a ghost, okay? Because propagator will be modified to k to the fourth, okay? If you go from k squared to k to the fourth, no matter what it is, ADS, whatever, I mean, second pole will be a ghost, okay? One of these poles will be a ghost.
Not really. I mean, that's what I talked about yesterday. The fact that the residue is negative does not mean that the states are negative.
No, I mean, I stay on the, let's say, canonical picture, okay? Canonical, from a canonical, let's say, point of view.
What do you mean by canonical?
Like I would take it from some old style book, not from your paper, but some old style book like Bogolyubov Shirkov approach. No, yes, very simple, very straightforward.
Yeah, look, like I mentioned yesterday, the issue is not whether the Dirac norm is negative. The issue is whether it's finite. And when you look at any quantum field theory book, they take it as a given that the states that you start with are indeed a finite Dirac norm. And you don't know that until you construct the Hilbert space. And what Carl Bender and I did was we constructed the Hilbert space and we showed that the Hamiltonian was not self-adjoint in the space where you think you have the negative norms.
No, I understand. I understand what you are saying, but I'm saying if I don't go to something else, if I don't modify my whatever writing and use the same operators in this picture, I believe that extra pole is a ghost, and because now we're discussing totally different questions.
You're presupposing that the residue of the pole is the Dirac norm, which you then say has to be evaluated with an indefinite metric. What I'm saying is that the Dirac norm is infinite. Therefore, it can't be the residue at the pole. That's the point. Something else has to be the residue at the pole.
Yes, this I understand. But you see, now we're discussing absolutely different question about if we assume it is a ghost, what it will correspond in a dual conformal theory in one dimension less, okay?
First of all, the propagator is not the same. It's an anti-de Sitter thing, and it would be more like some field with time-dependent mass, like that. Or
in
coordinate dependent mass.
No, in anti-de Sitter, not. It is maximally symmetric space, it's okay.
No, on normal de Sitter, it will be conformal time dependence. I mean, you have extra factor.
Look, if you want to say that there's a ghost when you have flat space, then you have a ghost for maximally symmetric spaces. If that's what you want to argue. Why, I mean, because flat space is maximally symmetric.
No. For me, it's clear that it will remain like it is. If I
Well,
declare it,
Actually, maybe you can just by hands introduce some term which is like curvature term multiplied by kinetic term of this ghost, and then it will be not a ghost anymore.
no, you see, you're changing the question. I don't say this. I don't want to modify anything. I just say that if I want to continue Luca construction. Luca told us in the morning that if I take stellar gravity, okay, no extra terms, just stellar gravity, but add also lambda, some miracle happens. And it was a very nice question. If you consider lambda negative, consider ADS, construct conformal dual theory one-dimensionless, what will be mapping of this ghost to this conformal theory? My answer is here would be, it's a totally astonishing question because I don't know what will happen, but I know that practically all these ADS CFT people start with unitary theory without any pathologies, okay? And now now the question, first of all, there is a question what to do with ADS CFT mapping when ADS is not a background of simple R plus lambda Lagrange. But on top of this, it's R plus lambda with a what at least before talk of Philip was believed to be a ghost. Okay, now we can if it's a ghost or not, it's different discussion. But still, whatever it is, it will be mapped to something not obviously clear. This is a question.
Okay, listen.
Well, your ghost is
very sorry that I couldn't get to Luca's talk yesterday. It was a bit too early. But what you've described makes it sound like the talk was very interesting.
No, what I described now was just a question after, because Luca did not consider any ADS CFT mapping or whatever.
Oh, okay.
It was extra question.
I guess.
Yes, and now we kind of.
And DS CFT is worse.
By the way, do we have speakers around?
Yes, we have
Jean-Luc Lehners is around. Good.
I am also around. I'm Laura.
Hello.
Hi.
Hi, Jean-Luc.
Good. Before we go to Alexei, before we go to the talks, do you want us to send you the slides? Do you want us to send? Do you want us to send you the talk?
Yeah, yes, it would be great because then I will be happy to upload them to the website. Yes, and arrange some list of slides. So Laura, you are also around. Laura.
Yeah, also here. David wants maybe make him co-host.
Where is Laura?
I'm here.
You're here. Okay, nice to meet you.
Nice to meet you.
Hello, David. I will make you co-host also just in case. Maybe you need some extra power to mute someone who asks too many questions.
I shall use it carefully. Okay.
No, actually speakers need to be co-host in order to be able to share slides. By the way, Laura, may I ask you, are you using Mac?
Yeah.
Can I ask you to try to share screen now? I know that you're not the first speaker, but can you just try to do it? Will you be able to do it? Yeah, you can do it. Okay, great. Thanks.
Let me just check that I can then do, because there is always the bar of Zoom on top of, how do you get rid of
this? You can take and move, I believe.
I can just pick it and move it.
Well, at least.
Yes. Okay, so good. Let me just try.
Yes. Okay, good. No, I'm asking this because yesterday it was an issue, like two people could not do it easily from their Mac computers.
Something is weird. No, okay, it's fine.
No, but you see now it's kind of up to your computer. Yesterday it was up to whatever strange communication between Zoom and Zoom, let's say.
Yep.
Good.
Can I ask you, how do you, how do you put a blurred background? In general, Zoom, how can I put a
It's
blur?
an option under preferences in Zoom.
Okay, thank you.
Yes, somewhere in preferences, I believe,
Background, yeah.
where there is
Blur.
virtual background, there is something like blur, at least to me.
Now it should be blurred, mine. Yeah. Okay, cool. As I asked to Sravan, if possible, I'd like my talk not to be recorded, if that's okay.
Yes, he told me I will just stop recording at this moment.
Perfect.
No question. I mean, it's up to you. You are the speaker. If you say no, it means no. Very simple.
So shall we, Jean-Luc, welcome. Do you want to try sharing check that you can share your screen, your slides?
I do.
Yes, surely you can try. Yeah.
Let me try.
Yeah. Great.
Yeah, that's good. Maybe.
Does that work?
What? Yeah, and indeed, that's in presentation mode, so that's all good.
Yes. Do you also see the little red dot, the pointer?
Yeah, that's right. We have your laser pointer,
Okay.
virtual laser
Good.
pointer as well. Good.
Yeah, so I guess Andre Linde will join a bit later. It's too early for him.
Yeah, no, that's right.
Well, there's a big time difference, so.
Yeah, especially between China and his place. Yeah, I believe in it. Yeah.
We're somewhere in the middle here in Europe at the moment then.
Yeah.
So
The times for Europe are actually the best, I think. No, they're the most convenient.
yeah.
Well, it depends how you adjust the timetable, you see. We could make it
Yeah, sure.
we could make it differently, but it's just averaging between speakers, I would say.
Right.
Yeah, that's why we have like the conference schedule is shifted for a few days. So more towards Chinese time, and then the last 3 days shifted towards Central European time. Yeah, but surely it's difficult to satisfy everyone.
It's a good compromise.
Yeah, I think so.
So shall we, are we ready to make a start?
Yeah, I think so. Yeah,
I will chair. I mean, if you're happy, Jean-Luc, I can keep an eye out for questions in the chat, and
Sure.
if people want to raise questions, they can do it that way during the talk, and I'll try to find a convenient point to raise them.
I'm also happy for people to just speak up. That's also fine.
Yeah. Okay. Good. Okay, so maybe we should get started with I was going to say the first talk of the afternoon, at least in Europe in the afternoon. So it's a pleasure to welcome Jean-Luc Lehners, and from the Max Planck Institute in Potsdam, AEI, and he's going to tell us about how to create universes with internal flux. Take it away.
Thanks, David. And thank you to the organizers for inviting me to this conference. It's a pleasure to talk. And what I want to talk about is essentially, well, mainly a paper that I wrote a few months ago with Kelly Stell and Rahim Leung from Imperial College, and which deals with this question of how one can create universes. This is based essentially on the framework of the no boundary proposal, and which I will introduce first. I also wrote a review about this topic recently, so if you want more details, you can take a look at that. Now, one way to motivate the no boundary proposal is to say, in cosmology, we always ask what happened before. And then we find out an earlier phase of evolution, and we again ask what happened before. And this can lead to a kind of infinite regression where we go to earlier and earlier times, but we always have to specify initial conditions at every earlier stage. And the idea of Hartle and Hawking was to just say that if the geometry of the universe is completely rounded off so that there is no earlier boundary, then we sort of avoid this infinite regression. At the same time, we actually avoid an initial singularity, because in standard hot Big Bang cosmology, of course, if we go back as far as we can, we necessarily reach an early singularity. Now, the way in which this is avoided here is by allowing the geometry of the universe to become complex. And in fact, if you have a Euclidean section at early times, then you can round the geometry off just like the surface of a ball. In a sense, then, this is the initial condition, right? Just the fact that the universe is rounded off this specifies the initial conditions, and then, well, the question you can ask is, is this in agreement with what we see in the universe? Now, the ideas were spelled out in much more detail in a famous paper by Hartle and Hawking from 1983. And there, the way they define the no boundary wave function is to say that you should sum over all metrics and all matter configurations which are compact and regular in the past. And moreover, one should, in the formal definition, one should sum over Euclidean metrics. Now, this wave function then is a function only of the final conditions. So if we go back here at the final time here at the top, that's where that you can think of as the conditions today, or maybe at some time in the early universe, but when the universe is already reasonably large, let's say. And the wave function will simply be a function only of these final conditions and not of any other initial conditions. That's because the initial condition is simply specified by this no boundary condition. That's all well and good, but then of course one has to make this definition precise. Now, the framework in which this proposal is formulated is the path integral. So, but the path integral for gravity. If we take the standard path integral in quantum mechanics, then if we calculate the amplitude to go from some space-time location A to the location B, we sum over all paths that link these two events. And if we do the same for gravity, then really what we are calculating are transition amplitudes usually between two spatial slices of the universe. And then we would sum over all geometries that connect these two slices and all matter configurations that connect them. So really we have a sum over geometries, and this is something that it's not obvious how to calculate. Again, this is something that has to be made precise. Also, an issue that is a little contentious in this context is how to calculate probabilities. Because in standard quantum mechanics, of course, we just take mod psi squared as the probability density, but and this is a conserved probability. But the point is that when gravity is included, in fact, mod psi squared is not conserved. It is rather the Klein-Gordon current that is conserved, and there have been many debates about how to properly define probabilities. I will get back to this question later on. So what we attempt to do is to calculate this path integral. Now, in many situations of interest, it can be usefully approximated by a saddle point approximation. This is because h bar is small, and so basically the integral is well approximated by the saddle points, meaning the points where the action is stationary. Now, because the action is stationary, this also means that one can approximate the path integral by using solutions of the classical equations of motion. The only thing that's new here, compared to sort of classical mechanics, is that these solutions are now not necessarily real solutions. In fact, it turns out that the no boundary conditions do not lead to real solutions, but can only be satisfied if you extend the solutions to complex solutions. So basically what we will do is solve the classical equations of motion, but allow the fields to become complex. And these no boundary solutions are sometimes also called instantons, or sometimes they are called fuzzy instantons because they are complex. Now, the simplest example of a no boundary solution occurs for pure de Sitter space, when you just have a cosmological constant and no matter content. Now, the standard solution, standard de Sitter solution in a closed slicing is hyperboloid when viewed from a higher dimensional spacetime. So this hyperboloid reaches a minimum radius and then re-expands. So normally it contains a bounce. However, one can sort of end the classical geometry at the minimum size, at the waist of the hyperboloid, and then glue onto this the Euclidean version of the solution. One gets the Euclidean version by simply letting the time coordinate go to imaginary time by doing a Wick rotation. And then the solution, the Euclidean solution, again with constant curvature, is just a sphere. So when one can, in fact, glue half of a sphere at the equator to the waist of the hyperboloids, and in that way obtain a solution that is continuous and also has a continuous first derivative at the gluing. If we picture this solution as a path in the now complex time plane, then if tau here is the Euclidean time, one would start at 0 and evolve along Euclidean time first, along the purple curve that corresponds to the sphere part of the solution. Then one would make a 90-degree turn and now go in the Lorentzian direction. And in that direction, the solution becomes then the Lorentzian de Sitter solution. Once we add a scalar field, things get a bit more complicated. This is because, let me give you an example here. I'm just plotting the solution again as a function in the complex time plane. Left here is a graph for the scale factor A. On the right is a graph for the scalar field. The dark line is the line where the fields take real values. Now, if we just plot the solution for some random initial value for the scalar field, this is typically what it looks like. Now, what we want, although I said that we allow fields to take complex values, certainly at the final time. So today when we measure the universe, the field values should be real, right? Because these are the actual physical values that are being measured. So at late times on the final hypersurface, the field values must be real. This means that if we look at this solution in the complex time plane, it means that at some point, probably late in the Lorentzian direction, both the scale factor and the scalar field must be real simultaneously. And you see, this does not happen for these solutions. If you would overlap these two graphs, these two black lines would not coincide anywhere. So there is no, so basically for this solution, one just doesn't get one just doesn't get a solution with the required boundary conditions. What one has to do is one has to tune the value of the scalar field at the bottom of the no boundary solution. So sometimes this is called the south pole of the solution. So if I go back to this graph, here the point at the bottom is often called the south pole. And one can tune the value of the scalar field there such that, in fact, you see now these two black lines start overlapping if you were to put these graphs on top of each other. So what this means is that if one tunes the value of the scalar field appropriately, then one obtains a solution where at late times it really turns into a classical Lorentzian solution, even though at the beginning it's a complex solution. And it turns out that in order for this to happen, you need a dynamical attractor. In the present case, I used an inflationary potential. And so inflation provides the necessary attractor for this to happen. Basically, the attractor ensures that when one of the fields becomes real, the other one also becomes real. So the attractor drives you towards a classical solution. So this is, yes.
So,
Sorry, question? Sorry, I think you were muted.
hello, can you hear me?
Yes, now I can.
Yeah. Well, my question is, if you start with Euclidean space-time, and
Yes.
you can also equally go to ADS, how do we avoid that?
I can go to what? Sorry?
Yeah, ADS space-time can also be emergent in the late time, because you want to go to Euclidean, from Euclidean to de Sitter, which makes sense because it is de Sitter universe is good. We can explain observations with inflation, but it's also possible that when you are Euclidean spacetime, emergent universe can be ADS, but we don't want that. How do we avoid it from?
Well, here the potential is positive by assumption. So in fact, the solution automatically turns out to be close to the sitter.
Okay.
So you can do the same kind of calculation, in fact, with a negative cosmological constant or a negative potential, and then indeed the solution will be ADS or in some cases Euclidean ADS. That's true. But this depends on the theory that you choose to start with.
So there is
but you're right, but very similar calculations can be done with a negative potential, and then one gets spacetimes which are typically sort of close to Euclidean ADS, and they don't involve time evolution in that case. Right. In fact, the solution is typically sort of a Euclidean solution, and it's useful for studying Euclidean ADS CFT, for instance, but it does not give the required time evolution that we want in cosmology.
Okay. Thanks.
Now, so this was just to show you that these solutions exist, solutions with the required boundary conditions exist, but there's a more basic question, which is how should the path integral actually be defined? And there is an issue which has to do with the uncertainty principle, and it can be seen from looking at the Friedmann equation. So if we look at, here is the Friedmann equation in a closed universe with positive spatial curvature. That's why there is this +1 term here. And I'm assuming a scalar field phi, and there could be other types of matter that don't concern us right now. Now, if the idea of Hartle and Hawking initially was that one should focus on geometries that are compact and regular. Compact means that somewhere, and that's this south pole of the solutions, somewhere A is equal to 0. And regular would mean that when A is equal to 0, the Friedmann equation is still satisfied and does not blow up. Nothing becomes infinite. Regularity then means that one would want A dot squared +1 to be 0. And that's actually just the same as saying that the geometry starts out Euclidean. So A dot is plus or minus I, but really then A comma tau, where tau is the Euclidean time coordinate, is plus or minus 1. Now, the thing is that really one cannot really fix both A and A dot simultaneously because these are canonically conjugate variables. The uncertainty principle forbids this. And so really when one defines the path integral, one has to choose either to impose compactness or regularity, but one cannot just impose both at the same time. And it was typically thought that one should impose compactness as a condition. So one should actually sum over all geometries which start at 0 size. In the following, I will denote the square of the scale factor with the letter Q for a reason that will become clear in a minute. So we will now at first impose the boundary condition that Q is initially 0. So we're summing over compact metrics. And we're taking the simple system of just having gravity and the positive cosmological constant lambda. The metric, as I said, we call the scale factor squared Q, and also we will rescale the time coordinate in this particular way. N here is the lapse function, which determines the time that is evolved. We will take the time coordinate t to run only between 0 and 1. So we'll have a fixed range for the time coordinate, but then the actual time will be determined by the lapse function n. And this time part of the metric is rescaled by a factor 1 over q. This has no particular physical meaning, but it has the great advantage that the action becomes quadratic in Q. And so, in fact, the path integral, which is now an integral over Q and over the Laplace function n, in this path integral, the integral over Q can now be done exactly because it becomes simply a Gaussian integral, because since the action is quadratic in Q. And this greatly simplifies the analysis. So one can just do this integral over Q, and one is left with an integral over the Laplace only. And this integral over the Laplace is a bit complicated. It's given by this expression here. I should say Q sub 1 here is the final value of the scale factor. So we interpolate between size 0 and size Q1. And this integral, because it's complicated, again, we can approximate it by a saddle point approximation. And one can then easily determine that there are 4 saddle points to this integral. These saddle points are complex, which is a reflection of the fact that one cannot find a real solution of the Einstein equations which satisfy the no boundary condition. And so really what we will do is estimate, well, use an approximation scheme, which the formal theory for this is called Picard-Lefschetz theory, but we will not need all of this machinery here. We'll just try and look at what these saddle points look like and how one can define the integral with respect to these saddle points. Now, actually, let me make one remark, which is important for later considerations, which is that these saddle points, as you can see here, these signs here can all be chosen arbitrarily. The fact that there is this plus or minus I here means that these saddle points can be thought of as occurring in complex conjugate pairs. And these complex conjugate solutions are closely related, but they have one very important difference between them. And the difference is the following. So really, what it means, this complex conjugation implies is that the way in which the Wick rotation is done in going from the Euclidean to the Lorentzian section switches sign. So it's basically as if one can think of this as one value of the Laplace giving the standard Wick rotation that we're used to in quantum field theory. And this leads to stable perturbations. So perturbations which have a Gaussian distribution. And the other sign will give the opposite Wick rotation. And this leads to unstable perturbations. So this leads to perturbations which are weighted by an inverse Gaussian, meaning that larger perturbations, here the amplitude is denoted by little h, larger perturbations really would be more likely. And so a universe like that would not be homogeneous and isotropic, but would be as curved as possible. Of course, really what it means is that the calculation becomes out of control, right? This becomes an untrustworthy calculation, and if one adds perturbations, and the approximation of looking at approximately homogeneous and isotropic space-times breaks down. So in a sense, what one can think of is that one type of saddle point is stable. The complex conjugate type of saddle point is unstable. One can then ask in this path integral, which kind of saddle point is picked up? For this, we need to look at the steepest descent contours. The integral really has to be defined on the steepest descent contours, which are associated with the saddle points. There are these 4 saddle points in orange here, 1, 2, 3, 4. And I drew the steepest descent lines in black with the descent direction always indicated by the arrow. So the arrow points downwards, meaning that that as you follow the arrow, the weighting of the integrand becomes smaller. And if we define the integral, here, this shows the plane of the Laplace function, where the Laplace actually is defined such that real values of Laplace correspond to Lorentzian spacetimes. So in this graph, the horizontal line here in the middle corresponds to Lorentzian spacetimes. The vertical line would be Euclidean spacetimes, and the other points are complex spacetimes. So if we define the integral as a sum over Lorentzian spacetimes, that would be along this orange line here. Now, this orange line can be deformed into this steepest descent contour J1, which runs through saddle point 1. The colors in the background basically are color-coded to indicate regions of convergence, of divergence of the integral. So the regions which are green are regions where asymptotically the integral is convergent, and so represent regions over which one could define the integral. So one could define the integral over a contour that ends up in these green regions. Whereas the red regions are regions where asymptotically the integral is divergent. So really here, what one can do, oh, and I should say yellow is just in between, where really the weighting is in between values at these two saddle points that are adjacent to this region. Now, so in the present case, if we had the Lorentzian integral, it could be deformed into one that passes only through saddle point 1. And in fact, the arc here at infinity gives 0 contribution, as one can fairly easily show. Now, the trouble is that this saddle point 1 is one of the unstable ones. So the stable ones turn out to be in the lower half plane, and the unstable ones are in the upper half plane. So the trouble really is that one picks up a saddle point which is unstable. So if we define the no boundary path integral as a sum over compact metrics, and if the integral itself is defined by a sum over Lorentzian metrics, then this gives an inconsistent result. But you could say, okay, but Hartle and Hawking initially proposed that really one should sum over Euclidean metrics. However, as you can see from this graph, the Euclidean integral along this vertical line always contains these red regions of divergence. So the Euclidean integral actually is fully divergent and doesn't actually exist. So that means that that's not an option either. Now you could look for other contours, but the problem is that whenever you have a contour that includes a stable saddle point, like the one here numbered 4, you see there is a steepest descent path that links it to an unstable saddle point. So whenever you pick up a stable one, you automatically pick up an unstable one as well. And this renders the calculation ill-defined. And there has been a whole debate about this issue. I will not go into that today, because there's actually a sort of an elegant way around this problem. The way around this problem is to recall that we made a choice by summing over compact metrics rather than regular metrics. And in fact, we can also instead now choose to impose a regularity condition, meaning that we actually impose a condition on the expansion rate of the universe. And the interesting thing about this is that this expansion rate is Euclidean initially, because that implements the no boundary condition. And because it is Euclidean, it automatically fixes the sign of the Wick rotation. So the sign of this initial momentum, whether this is plus or minus I, fixes the Wick rotation. And if we choose it to be plus I, that corresponds to the standard Wick rotation, which gives stable fluctuations. In fact, what happens if one defines the integral that way, one can follow, again, the same steps as before, and one obtains an integral for the lapse and so on. Interestingly, this now only has 2 saddle points and only the stable saddle points. The other 2 saddle points, which were in the upper half plane, have simply disappeared. And so now the integral automatically becomes an integral over that picks up these stable saddle points. Moreover, at the saddle points, the initial size of the universe is 0. So compactness is also achieved, but only at the saddle points. So this suggests that actually it's better to define the no boundary path integral as an integral with an initial momentum condition instead of an initial condition on the size of the universe. There's another nice feature is that if one expresses this definition directly as a condition on the Wheeler-DeWitt equation, if one uses the Wheeler-DeWitt equation and imposes this no boundary condition as a momentum condition, then in fact, what one is imposing turns out to be that the derivative of the wave function with respect to momentum is 0 at the no boundary point. And this is the same as saying that actually, we impose the operator condition that corresponds to saying the size of the universe has to be 0. So this momentum condition, which is also called a Neumann condition, can be seen as the momentum space equivalent of the 0 size condition. And it can also be interpreted as saying that there is no momentum flow into or out of the universe at the creation of the universe, which is very much in the spirit of the no boundary proposal, because it means that the universe is in a sense completely self-contained. Nothing flows in or out of the universe. There is no boundary, and the universe is just, that's the full extent of the space-time. So in a sense, this all fits together pretty well. One would then calculate probabilities from looking at a sequence of such no boundary instantons with larger and larger values of the scale factor. And in fact, then one can show that in such a case, if the wave function becomes of WKB form, and in fact, mod psi squared is an approximately conserved probability, so one can use this to assign probabilities, at least in an approximate way. Okay, so just to recap that what one finds is that the no boundary wave function gives can be approximated as a saddle point approximation. The amplitude of the wave function is given roughly as e to the 1 over the potential. So it prefers small values of the potential. And one of the main consequences is that the perturbations are automatically in the Bunch-Davis state. So this condition, this no boundary condition automatically imposes that the perturbations start out in their ground state. That was it for a brief review. Now I want to get to the actual topic of universes with flux. Let me just motivate this briefly by recalling that in string theory, we typically have extra dimensions. And these extra dimensions, the geometry of the extra dimensions can lead to, for instance, the gauge groups that gauge fields will see in the large dimensions. And so they provide a way of unifying geometry and particle physics. And anyway, they are one of the nicest and most interesting aspects of string theory. Now, these extra dimensions in a cosmological context, they have to be small and stable, because coupling constants typically depend on the size and shape of these dimensions. And if they were varying, then we should have seen variations of coupling constants over the course of the history of the universe. And so far, there are no indications that such variations occurred. So if such extra dimensions exist, they must be stable. Now, one way to make them stable is to include fluxes, which are generalizations of electromagnetic fields. Now, one of the features in string theory is that these fluxes are typically quantized. Let me give you a brief argument for why this is the case. One quick argument arises if you assume that branes exist. Branes can carry the charges that are associated with these fluxes. And basically, the brane action contains a term which has the gauge field, the P-form field, integrated over the world volume of the brane. And one can, if you now calculate an amplitude, this will appear in the exponential. And you can calculate, let's say the brane here has world volume sigma, which is a sphere or a circle in this case. one can use Stokes' theorem to actually calculate this flux term either over the upper hemisphere or the lower hemisphere. But if these two calculations are to give the same result, one can show that, in fact, the integral over the full sphere should not contribute to this. And this does not contribute only if the integral over the flux is proportional to 2 pi n, where n is an integer. You see, because then you get an e to the 2 pi I term here, which is simply 1. So there is no ambiguity in the amplitudes as long as the fluxes are quantized. But this poses a problem, or a puzzle at least. If fluxes are quantized, you know, how do you get them? Because you cannot turn them on with, you know, step by step. You cannot turn them on incrementally. As they have quantized values. So you have to somehow create the flux already. And so the question is, how can one create a universe with flux? And is this compatible with the no boundary idea of creating a universe? We can analyze this in a toy model. This is a model in 8 dimensions, studied by Ketov and by Otero and collaborators, which is kind of an equivalent of Starobinsky's model of inflation, but in 8 dimensions. So one has gravity and then r to the 4th, in this case, correction term, not r squared, but r to the 4th, and also a 4-form flux. Let me just note that these ingredients, r to the 4th corrections and 4-form flux, are actually present in 11-dimensional supergravity. So the model is not completely crazy in that sense. And what one can do is now do in the same way as for the Starobinsky model, one can do a conformal transformation on the metric to get an gravity scalar theory. So there is now an extra scalar field phi from this, and we can dimensionally reduce from 8 to 4 dimension on a 4 sphere. This introduces a second scalar field chi, which determines the size of the 4 sphere. All of the coefficients here, these numerical coefficients, are chosen such that these scalar fields are canonically normalized in 4 dimensions. We will also have flux on the 4 sphere, and this flux is proportional to some number, n4, which is proportional to an integer. Okay, so now one gets in 4 dimensions, one gets a theory of gravity with 2 scalar fields and the fairly complicated potential, which I've drawn here for a particular value of the flux n4. So the shape of this potential depends crucially on the flux. Let me illustrate to you how this works. So really this r plus r to the 4th part gives an inflationary potential for the scalar field phi. This is really the equivalent of the Starobinsky model. And the flux part gives an extra contribution in the transverse direction of the potential. If there is too much flux, then we have a runaway direction. So then this, even though there is an inflationary flat part for phi, in the transverse direction, the potential is steep and the field will just roll off in that direction. If the flux is too small, you see then the minimum of the potential is at negative values, and one will not get inflation. And in fact, if there is no inflation, then there are also no boundary solutions because there is no attractor. As I said earlier, one needs a dynamical attractor to get no boundary solutions because one needs to achieve simultaneously real field values at late times. And so there is sort of an intermediate range of flux given by this orange curve in the middle, where there is a local minimum in the transverse direction. And you see now at this, because this extra direction is the size, can be thought of as the size of the internal sphere. If you reside at this minimum, then this extra sphere is actually stabilized, which is precisely what we want. We want the extra dimension to be stabilized. And in the transverse direction, we have an inflationary plateau. And in that case, one can find no boundary solutions. Here's an example of such a solution. At the bottom, I'm plotting the field values for the scale factor A here, real part in blue and imaginary part in orange. You can see that the real part grows and starts growing exponentially, whereas the the imaginary part goes to 0, as it should. For the scalar field, actually, it's a similar situation, that it starts out with a non-zero imaginary part, so it starts out complex, but then it reaches real values at late times. And so these solutions exist. As long as the flux is in a certain range, which is given here in the present example, this is just a numerical example. But of course, there will be sort of discrete values of N4 in between this range. Now, one can then check and what happens when one varies the amount of flux. And if the flux is smaller, the potential actually is lower. But as long as there is a plateau still at positive values, one can find no boundary solutions. And it turns out that these solutions with lower potential have a higher probability. This is a general trend in the no boundary proposal. So in the end, really what one gets is the following. Here I'm plotting the probability as a function of the flux. And the flux really is quantized, so one should only think of it as existing at these sort of discrete values. If there is very little flux, then the potential is negative and there is no solution. If there is a lot of flux, then no boundary solutions exist, but they decompactify. There's a runaway direction and the internal manifold is not stabilized. So really what one finds is that there is sort of an intermediate range of flux, which does give no boundary solutions and has stable internal dimensions. And so in this way, the no boundary wave function selects a certain range of flux, which is compatible with a universe like ours. And so really it provides a probability distribution on solutions and on parameters of the solutions, like the fluxes. In other words, what this shows is an example of how the no boundary wave function can be a kind of a filter on the landscape of solutions. If there is a landscape of solutions, this does not mean that these solutions actually can correspond to universes that exist. With the no boundary condition, this can only occur if there is the necessary dynamical attractor for this to happen. And so even if string theory contains a vast landscape of solutions, then cosmology here in the form of a no boundary proposal can act as a very strong filter on this landscape of solutions and keeping only some of the solutions allowing only some of these solutions to turn into actual universes. And I think this is sort of a general conceptual framework that is worth exploring, because it might, in fact, show that the consistency conditions for a universe to exist are much stronger than what was initially thought. And this was the main point I wanted to make in this talk. I think in view of the time, am I right that I'm nearing the end of time?
Yeah, that's right. If you've had 40 minutes, and so if you want 5 minutes for questions, anyway, yeah.
Okay, good. Then I think, I had some more slides, but then I think I might as well, since this was the main point, I will end here. Thank you very much.
Okay, thanks very much, Jean-Luc. I wasn't cutting you off there, but
no, it's fine. I just think it sort of makes more sense to leave time for discussion.
Indeed, I'm sure there will be questions, and Sravan's first to raise his hand. So, Sravan, you had a question?
Hi, Jean-Luc. Thanks for the very nice talk. I have a couple of questions. First one is very short. This flux compactification you're talking about, is it at the Planck scale or larger than the Planck scale?
Well, this actually, the size will depend on the parameters of the solution. For instance, it depends on the charge of this flux, of this P form. So it can be it should be much bigger than the Planck scale, but of course still microscopically small. Otherwise, we would have seen such dimensions. Also, I should say this is just a toy model, right? In general, the internal manifolds are much more complicated than just spheres. But it's a toy model to illustrate just the main process here.
Yeah, my second question is exactly related to this toy model. Do you change significantly your results if you include R squared term?
Yes, in fact, in this model, one needs the R to the fourth term in order to get this flat region in the potential. So it turns out if you generalize the Starobinsky model to arbitrary dimensions, you need an R to the D over 2 term. So in 4 dimensions, you need R squared. In 8 dimensions, you need R to the 4th. In 22 dimensions, you would need R to the 11th.
Okay.
So that's the only term that gives a flat plateau. So if you add an R squared term with a sort of reasonably big coefficient, it will destroy the plateau.
Well, then you have difficulty to connect it to Starobinsky inflation in the later evolution of the universe, right? Because I mean, Starobinsky inflation is in 4 dimensions with R squared term. So I'm wondering if you can connect this smoothly.
Right. So what I did here was to first go to Einstein frame and the scalar field case in 8 dimensions, and then dimensionally reduce. What you're saying is one could try the opposite, first dimensionally reducing and then changing to Einstein frame.
Yeah, exactly.
Yeah. So I think in that case, one would indeed get the kind of Starobinsky term first, and then one would go to Einstein frame.
Yeah.
Yeah. But this was technically it's easier to do it the way I just did it, to go to Einstein frame first.
Okay, I understand. Thank you.
Thanks. And there's a question from Philip Manheim.
Yes. Thank you for the presentation. There's one thing that I was a little bit puzzled over. You had a nice, well-behaved path integral, one of the stable solutions earlier on, where you integrated over all homogeneous and isotropic possible cosmologies. But is that a complete basis? I mean, wouldn't the basis for the measure also include inhomogeneous cosmologies anyway?
Yeah, so
I don't see how you can restrict to homogeneous and isotropic alone.
Right. So this was a choice initially. So this is the basically I chose to. So it's a drastic reduction of the number of possible universes that you sum over. This is the mini superspace. Mini superspace approach, where you basically I summed over only homogeneous and isotropic universes, but then afterwards you can add perturbations perturbatively to check whether that was a reasonable thing to do or not. And I would say if the perturbations turn out to be suppressed, then this justifies this approach, because it says that the perturbations indeed will not make a big difference. Now, on the other hand, if you find that the perturbations are enhanced, then you know that this approximation was definitely wrong. I mean, that this was definitely a bad approximation. So it's sort of something that you have to check at the end of the calculation, whether this was a reasonable approach or not.
Thank you.
Okay, and maybe one final question then, George Thanaras.
Thank you for the great talk. So in the context of an eternal inflating universe, the universe loses memory of the initial state. So I was wondering if you had any idea how these ideas of the initial conditions for the universe can be related to observation.
Well, this depends on, so I am, I guess I am explicitly assuming that eternal inflation does not occur. Whether eternal inflation actually can occur or not, I guess, is still up for debate, right? It's not really known. In simple, of course, in simple 4-dimensional models, it can easily occur. On the other hand, if you calculate the semi-classical wave function in an eternal inflation model, it will blow up. The action in fact becomes infinite, which might be one indication that this is simply not allowed. Another one is if something like the swampland conditions turn out to be true, then well, they require the potential to be so steep that in fact eternal inflation cannot occur. Now, I think it's not really clear yet, right? How this will turn out. It's true that if eternal inflation can occur, then all memory of such an initial no boundary state will be lost. You can still then ask the question, you know, how did the universe come into existence in the first place? But it will be then not really something that can be checked by observations, because it will be, there will, you know, if you have a large number or infinite number of tunneling events in between, you will not have any memory of that, presumably.
Yes, thank you.
Okay, I think we should move on at this stage, I guess, and let move on to our next speaker. We'll have a discussion session at the end if people can hang around. Jean-Luc, are you available for the discussion at the end?
I unfortunately have to go and take care of my children because my wife is working later today, and I can stay for some of the talks, but then at some point